In the year 1596, Johannes Kepler published his book Mysterium Cosmographicum, in which he proposed that the distance relations between six known planets at the time could be explained by a model made up of the five Platonic solids. The core assumption of this model was that the planets revolved around the Sun in circular orbits, and this was the predominant view of the period. Circles were perfect, and a perfect God created the planets. Hence, planetary orbits must be circular. In fact, prior models explained the available measurements to within precision error at the time. In 1600, however, Kepler met Tycho Brahe, and in 1601, he gained the access to Tycho's latest observations of Mars, and he soon realized that even his most advanced circular motion model produced a deviation of 8 minutes from Brahe's data. It took him at least 4 more years to finally realize that Mars did not move in a beautiful circle. Rather, the orbit had to be an ugly ellipse. While Kepler eventually accepted this model, his contemporaries did not mince words. Yikes! Now, I am no astronomer or theoretical physicist myself. I find ellipses to be beautiful, in fact. Circles are often boring and simple to deal with. But Kepler did not model the orbits as ellipses because he found them beautiful. Ellipses were validated by the best available data at the time. Today we have much better data to know that he was right. But if he had listened to his contemporaries and decided the orbits had to be beautiful, he would have been stagnated. And that is the point Sabina Hossenfelder makes in her 2018 book, Lost in Math: How Beauty Leads Physics Astray. She claims that modern physics is stuck because the physicists are busy looking for a beautiful mathematical model, a criterion too subjective to be scientific.
The more beautiful your theory is, the more it will generalize to the future.
In high school, I was struggling to learn the Schrodinger wave equation, which was horrible. It was ugly. And I said to myself, how can God be so malicious to create the Schrodinger wave equation?
So it makes sense that we like it, but does it make any sense that we expect nature on the most fundamental level to appeal to this very sense of beauty that we take from apples, basically?
Mathematics has likely been applied to physical science since the time of Archimedes, if not earlier. Once Kepler figured out that planets revolved in elliptical orbits, he was able to make predictions of their paths using mathematical calculations. Ultimately, mathematics just provides us a way to unambiguously state what we know, what we assume, and what we logically conclude from these. While the book's title might suggest that Sabina is against math or against relying on it to discover new theories, that is not the case at all. Pretty much from the get go, she describes how math has been useful for making predictions such as the existence of the neutrino, the Higgs boson, and gravitational waves. The work of a theoretical physicist in the last few decades has been to come up with a theory of everything, a single theory to describe the fundamental particles, particles that make up everything but are not made up of anything else. The question then is, how does one find these particles? This is where the math comes in. A theoretical physicist comes up with a theory, which is a set of assumptions to add to the knowledge we already have. Then, using math, we see whether this theory is not contradicting what we already know and matching all the observations we already have. Now, the next step becomes predicting what we don't know yet so that the experimentalists finally have a hypothesis they can try to verify. How does one decide upon a theory? How about a beautiful one? Throughout the book, Sabina has added quotes from her interviews with top theoretical physicists to try and gather what they mean by beautiful. She describes three aspects of beauty: simplicity, naturalness, and elegance. And I get her frustration. These terms are not much less vague than just saying beauty. How is a model defined to be the simplest? A 2D approximation of a 3D system is simpler. but it is not more accurate. So where does one draw the line? To her credit, Sabina does manage to at least provide some examples to help us understand what her colleagues mean when they use these words, which brings us to the main target of her attacks. The Standard Model is the proven but incomplete theory of fundamental particles. There are particles that are classified as matter particles or fermions and force particles or bosons. Supersymmetry is a theoretical framework in particle physics that proposes a symmetry between fermions and bosons, stating that for every fermions, a superpartner boson exists and vice versa. But more importantly, it meets the beauty criteria for theoretical physicists. Of course, it also predicts the various properties of these particles, enabling hypotheses to verify their existence. And to validate these hypotheses, the Large Hadron Collider was built at CERN with a budget of over $10 billion. Okay, fine, it was not built for this purpose, it was built to find the Higgs boson. But after they found the Higgs boson, they got a lot of hope and decided that they could probably validate supersymmetry. Spoiler alert, they did not find any of these particles. Not when Sabina's book was being written, not even today in 2026. In fact, now physicists have lost hope that the correct theory will be natural according to their criterion, and supersymmetry is facing a crisis with weakened research activity. Now we come to the main purpose of this video. Do I recommend this book for reading? Sabina uses very simple English and her writing style is very conversational. She makes excellent use of exclamations and pauses in a manner that you might be able to hear her voice if you have watched any of her videos. The text is interlaced with wit and humor, but she does come off rather preachy in certain sections. While she uses great analogies to explain various concepts for a layperson, she does seem to dumb it down too much to be able to actually get any understanding of the concept. She is able to convey the main point of supersymmetry, which is the existence of superparticles, but she is not really able to convey why she feels that their existence is so ridiculous to her. In chapter 3 to 9, it begins to feel like she is making the same point over and over again, and at some point, instead of the investigation she claims it to be, it begins to feel like a manifesto. She also comes across quite cynical about the value in upgrading of the LHC to run at faster speeds. While LHC has clearly failed to verify supersymmetry, it has provided much more precise measurements of the already known particles. Sabina has not acknowledged the side effects of the development of the technology for this upgradation, such as MRIs have advanced due to the advancement in superconductors. Computational fluid dynamics and machine learning have advanced due to the advances in grid computation, and so on. However, I would still recommend that you read it because she does a very good job of letting us into the mind of a theoretical physicist. The book is also very educational in terms of detailing how math and science are not the same but rather complementary. And in the last chapter, she mentions various biases that all scientists need to be wary of. After all, even though Kepler was able to accept that the orbits were elliptical, he did not give up on his Mysterium Cosmographicum. Rather, he modified it to come to some strange conclusions that sound ridiculous to hear today. Whether or not you agree with Sabina that physics is lost in math, her book is a reality check. Math is not the universe itself, it is merely a tool, a language to help us find out more. And finally, don't expect the universe to provide us a pretty explanation.